Hello, my name is Tim Stewart. I am president at Visual Decisions, and we are here today to talk about modernizing root cause analysis with Industry 4.0. At Visual Decisions, we've been in the business of utilizing information from the shop floor to improve continuous improvement since about 2002. Implementing Industry 4.0 or digital transformation technologies can help drive great improvements in operations. Our customers have seen dramatic improvements, such as 30% increases in OEE, 50% scrap reductions, and more. But just like wearing a Fitbit doesn't automatically make you thin, implementing technology for Industry 4.0 won't automatically make the business better. The culture of the organization and the business processes have to be adapted to take advantage of those new capabilities to drive real improvements. This is why we have a unique approach to combining the smart factory and the lean factory to create a real-time lean environment. We work with our customers to adapt the processes to take advantage of the new capabilities and help our customers establish a true data-driven manufacturing culture. As a quick procedural note, if you have questions during the presentation, please enter them into the Q&A. I will get to them at the end of the webinar. Thank you. The agenda for today is straightforward. We'll take a quick look at what is root cause analysis and what is Industry 4.0. And then we'll go through some of the details of the different frameworks of a typical analysis and how we can improve those using Industry 4.0 technologies. So what is root cause analysis? In any improvement process, once the problem is well defined, an investigation must be performed to understand what are the key factors that cause or exacerbate the problem. Root cause analysis is the process by which those factors are determined. One key thing to note is that most issues have more than a single root cause. And the other key item to note is that the goal is to find causes to which actions can be taken to either eliminate or mitigate the underlying causes of the problem. So on the right side of the screen, what we see is a graphic from Jeffrey Liker's seminal book, The Toyota Way. And where we find root cause analysis in here is actually in the center section that he labels as cause investigation. And we can see it's asking why 5 times, which we'll get to in a minute. So what is Industry 4.0? Well, Industry 4.0 encompasses a lot of different technologies. The graphic on the right side is a visual from the World Economic Forum that is a comprehensive look at the different technologies that are considered to be part of Industry 4.0. At the center are some of the mainstream technologies that are out there today. And in the outer rings, we see things that are either maturing or just emerging right now. So it has different categories, such as advanced materials, production philosophies, analytics and intelligence, and so forth. So as you can see, there are a lot of different technologies that are part of Industry 4.0. What we're going to be focusing on today are some of the technologies that we have highlighted up in the upper left. And these are things such as advanced analytics, and the industrial Internet of Things, artificial intelligence and machine learning, and augmented reality. These technologies are very applicable to improving the root cause analysis process. So next, we'll look at several forms of root cause analysis. We'll start with some of the most basic and progress towards more analytical processes. So there are many frameworks for performing root cause analysis. Not listed here, and kind of the most basic is simply treating the latest symptom of failure as the root cause. This is essentially blaming the dog for barking instead of trying to find out why the dog was barking. So in the next several slides in this section, we will quickly review these different methods and discuss some of the strengths and weaknesses of each, as well as how Industry 4.0 can impact the performance of those. So one of the most basic methods of finding the cause of problems is to ask the 5 W questions plus the 1 H. I believe I learned this one all the way back in elementary school. When you want to find something out, you ask these basic questions to get to the bottom of the thing, bottom of things. Back then, though, we weren't taught to use data to back up the questions. We just tried to give answers to each question that made sense. We also weren't taught that there may be more than one answer to each one of those different questions. So this method can actually be very beneficial if done correctly. For example, if you are preparing to create charts of possible causes or perform a statistical analysis, this method can help you identify possible causal factors. It can also be used as a brainstorming tool to be somewhat comprehensive in the approach. However, it tends to lead to simplistic analysis as it doesn't get the practitioner to drill down any further than the top level causes. For example, it's not enough to know that my first pass yield went from 97% to 93%. Just knowing that my first pass yield dropped is not enough to take action on anything to fix it. So the information is not actionable. It is a good start, and I will know that I need to pay attention to it, and that's good to know. But until I know why it went from 97 to 93, there's nothing I can really do about it. To address that, in the old days, we went out to the line or machine or process with, either a set of tick sheets or a clipboard and a stopwatch, and we started watching the line for what was causing the defects or downtime or whatever problem might be. And so then, as we collected that information, making ticks on the tick sheet and so forth about what was happening, where they were happening, who was involved, and how frequently it was happening. That method of data collection not only lacked accuracy, but it also lacked detail. It was frequently biased, as we'll get into in a little while. But it was always wasteful to have those people out there watching the process and or taking time away from the process to make the tick marks and then aggregate that information and so forth. And there are much better ways to do that now. So when performing this analysis, Industry 4.0 provides capabilities to automatically capture accurate information about each one of these potential cause categories. Keeping with the example of first pass yield, information can be captured directly from the testing machines on how that part failed the test. The systems can know who is logged into the different stations. By knowing what machines were used for which parts, the system can know where the problem occurred. They will also know when that defect occurred. Finally, by tracking the detailed process variables as that part was processed, the system can track what happened during the production of those items and then start to correlate that to when those failures occur in testing. So using this data to understand what high-level causes are correlated to the problem can identify areas for further investigation, even if the who, what, when, why, where, and how don't necessarily drill down to the root causes. So then we get to the 5 whys, which is really lean manufacturing's favorite root cause analysis method. And in this method, we keep asking why until we get down to the root cause for the problem. In the example shown, our problem is that the customer is refusing to pay for the leaflets that we printed for them. Our top level reason is that the delivery was late, so the customer couldn't use the leaflets anymore. Instead of settling for that answer, though, we continue to ask why. We don't want to just blame the delivery guy for not getting there in time. In this case, the next question is, why was the delivery late? And we keep answering those and asking more until we eventually reach the root cause of the problem, that we ran out of ink and couldn't order additional supplies in time. At this point, we've reached a cause that we can take action on. We can put in a countermeasure to find a backup ink supplier that we can use in emergencies, so that when we continue to keep our normal stock minimized and have surge demand, we can have a place to go to get some ink during that surge. The biggest trap I've encountered with the 5 why method is that people only ask why once at each level. Kind of just like what we're showing here on the left side. There's only one explanation, there's only one answer for each of those why questions. The way that you really should do this is that you can end up with more than one answer to each one of those whys, and you end up with something that looks more like a tree than a straight line. The other problem that I've seen with this is that it's usually not done with data. It's usually done by gathering people together, either out on the shop floor or in a conference room, and asking people to go through that process just anecdotally. However, this method does lend itself very well to data collection, as we'll see in a little while. So the next method is the Fishbone or the Ishikawa diagram. And in this method, you show the problem to the right side of the diagram, over here in this little triangle on the right side. And then you try to determine all the contributing factors to the problem. It's typical, but not required, that the first branches in the analysis are man, machine, material, method, management, and environment, but they can be anything that is most appropriate. Then you ask what it is that's causing the issue. Continue asking why until the root causes are reached. So essentially it's 5 whys, but with a structure that encourages asking why more than once at each level. And again, this process is usually done in a very highly manual fashion that is disconnected from the process. Again, usually it's by gathering a group of people together and going through this anecdotally. Another weakness in this is that while the diagram gives a good idea of what are potential contributing causes, it doesn't show how much those causes contribute to the problem. So when data collection is performed, it's usually done manually after the initial analysis has been completed. Again, one way that it's done is to give the operators tick sheets or, having them walk away from the process to enter information into a spreadsheet or an Access database or something like that. And the other way is to have someone go out and watch the process and record that operation so the operator can continue their work. And one problem with collecting data by watching the process in person is the Hawthorne effect. People just behave differently when they know they're being watched. Think of how drivers slow down on the highway when they know there's a policeman on the side of the road. So this leads to problems of bias in the data. The data that gets collected does not accurately reflect how the process normally operates. With Industry 4.0, we collect data at all times. It's on 24 hours a day, 7 days a week. This allows us to create a Pareto diagram of how much each of the causes is contributing to the issue. Then we can begin the Kaizen event with a very strong data set on all of the different causes and how much they contribute to the problem and what's most important to address first. It's this very process that drove me to found Visual Decisions in the first place. I was doing lean consulting at the time and grew tired of looking at these processes and not having data at the beginning of the project. Then I would have to spend days or even weeks as that person that was out there collecting data on the shop floor. And, the other option is that they'd have these tick sheets when I started talking to them. And again, the tick sheets have a number of problems. If you're looking at downtime, they typically don't capture short stops. They typically don't have information on how long the downtime was for each one of the different stops. So you don't know how heavily to weight those different failures, et cetera. So we started implementing systems that would collect that data 24/7. Those systems provided such a huge benefit that I actually left that consulting company to start Visual Decisions. Since that time, we've focused on combining real-time data collection with lean practices to really bring the best of both of those two together. So just as an example, we worked with a bread manufacturer and worked with them to collect information automatically from the shop floor that, at the event level is, accurate, complete, and unbiased. And in this particular case, we used a homegrown system that they had developed to get data from at the machine level and persist it to a database. Then we helped them build an interface to analyze the information. In addition to the high-level aggregate information, we wanted to be able to drill down into the process to be able to analyze it and ask why several times for each different event. So for example, the interface was set up to analyze questions such as, why is the machine going down? Why are we losing time in the process? At the top level of the hierarchy is area here, and shows that equipment loss is the biggest contributor by far. And if I drill into equipment loss, just by clicking on that bar, it would go in and show me that the biggest category within there is oven. If I clicked on oven, then it shows me additional levels of detail. And one of the big things that I saw was that most days we didn't lose any time or very little time due to the oven. But then we would have these big spikes that would occur. And so what we wanted to do then was gather additional information. And it turned out that the best and most easy way to do that in this particular case was to have the operators enter comments when those particular events occurred. And so what we were able to do as we analyzed the information was that we found that the oven shelves were flipping due to broken pins on the conveyor. And what was happening is that these pins, as they would go through the oven and heat up and then come out of the oven and cool off, over time they would fatigue and eventually fail. So once we were aware of the issue and how big it was actually a very simple fix. We just put in a preventive maintenance program to inspect and replace the fatigue pins during an off shift. And just by having visibility to this, we were able to eliminate the single largest source of downtime and raise the OEE of that process by a significant amount just through that one change. And again, the change itself was very simple. Now, it would be easy to say that the customer should have been doing this in the first place, but until they had the data and saw how much time they lost, it just wasn't a priority. So they didn't have that visibility to what the real problems were. So the next way that we can look at this 5Y and so forth is graphical analysis. And this is essentially the visual and visual decisions. And so we saw some of the benefits of a visual approach in the last example. It's very easy to see, what were the biggest problems and drill down into those and so forth. The variety of different chart types that can be used to easily uncover many issues, they're difficult to see when you're just brainstorming in a conference room or looking at a page of numbers. In fact, being able to visualize information is at the root of why I called it visual decisions in the first place. So just as an example of that, if we look at these 4 data sets, it's very difficult to tell the difference between those. And this data set, or these data sets, were designed by a mathematician named Francis Anscombe. And so if you're following along, I'd just like you to take a quick look at them and see if you can see the difference between those 4 data sets. It's obvious to see that the numbers are a little bit different, but it's hard to tell exactly what we should be seeing from here. So if we use a statistical comparison of the data sets, we get the following. The mean of the X numbers are the same in every single case. The variance of the X numbers are the same in every single case. The mean of the Y numbers are again the same in every case. It's the same variance for the Ys. The correlation between the X and the Y is the same for each one of the different sets. The regression equation is the same for the different data sets. So are the data sets actually very similar then? And in particular, what's the nature of the relationship between X and Y? So at this point, we've looked at the raw data, we've looked at a statistical comparison of them, and it's very difficult to see anything. But if we put that on a scatter plot, we can immediately see that the data sets are indeed actually very different. So in one case, we've got a correlation, but it looks fairly random. And then in the other cases, we have very defined relationships between the 2 variables. And so just looking at these things visually, our eyes are extremely good at picking up on these trends and relationships and other important factors, where summary statistics and raw numbers just may not be able to do that for us. So when it comes to analyzing these things and being able to spot some of these important differences and so forth, being able to plot these things graphically as opposed to just kind of brainstorming what different impacts might be in different relationships can be a huge benefit. Just as another example here, we were working at a recycling company that was having issues with their furnace. And so the first thing that we did was create a run chart for their performance. In the top chart up here, you see that the thin red line was the set point, and the dots on that were the actual readings at different points in time. So ideally, every single one of the dots would be directly on the red line, as they kind of are in this segment here. So anything below the line is a performance gap called a dent, where the furnace wasn't producing the expected steam flow. The bottom chart simply shows the gap between the set point and the actual values as a measure of time. And this kind of chart can be very helpful to answer the question about when we saw different issues and be able to just eyeball and see if there was a recurring pattern. And in this case, it's pretty random and doesn't seem to be a driving factor. On the other hand, when we plotted that data as a scatter plot comparing the set point to the actual steam flow, the engineers were immediately able to pick up on something very interesting. The vast majority of the dents were occurring at particular set points. And while this wasn't enough to be directly actionable, it pointed them in a direction for additional research as to why those particular set points were causing issues. As a next step, what we did was we isolated what was happening during the dents to run correlation analyses on different process variables to the output, and then be able to eyeball those. So on the right side, we see, again, the statistics for the correlation metrics between the different measures. And then over on the left side, we're able to visualize that by plotting that on a scatter plot between any two variables. And so it was really interesting to see that you can definitely tell where the biggest correlation was by looking at the list of numbers here. But as you clicked through the different potential variables, looking at it on the chart, it was much easier to get an intuitive feel for what the relationship was between each of these different input or process variables and the output that we were measuring. Once we figured out what the biggest impact was, by the way, then we were able to put control plans in place to mitigate the impacts of that variability. So the next framework here is failure modes and effects analysis, or FMEA. And most anyone that's familiar with them will acknowledge the value of performing an FMEA. It's been around since the 50s and has been used to great effect for both products and processes. Performing one has generally involved not just gathering people in a conference room, but kind of locking people into a conference room for generally at least several days while they brainstorm and develop the results. It inevitably generates tremendous insights into the process, but it comes with an issue. The results of the studies quickly grow stale. The results typically get printed on sheets of paper and hung on a wall or put into a drawer. And then as the process evolves, nobody goes back to update the FMEA. And as downtimes and quality issues happen, nobody goes back to update the probability or severity of the different failure modes. And again, this is typically done by people estimating what those probabilities are, instead of actually utilizing the data to put those into the analysis in the first place. And it's typically disconnected from the way that people gather information on the shop floor. And in fact, I've yet to visit a single company that uses the failure modes that they've defined within their FMEA as the reason codes in their data collection system or their tick sheets or whatever out on the shop floor. And that disconnect just doesn't have to exist. With Industry 4.0, we can be collecting detailed information from the process that allows us to both identify new failure modes as well as to automatically keep the FMEA live and instantly accessible. And so by making that FMEA live and integrated directly into that daily process, it can become immensely more valuable to the organization. Finally, we close out this section with a brief discussion of kind of the gold standard of database root cause analysis. Some of the forms of statistical analysis that apply here are analysis of variance, design of experiments, linear or multiple regression, t-tests, chi-square tests, etc. It's beyond the scope of this particular webinar. We're already half an hour in to dive deeply into these statistical methods, but I do want to cover a few important points. These generally represent a test of hypothesis where the hypothesis represents a potential cause for the problem. In many cases, the preceding methods, whether it's 5Y or the 5 Ws and an H or whatever it is, can be used to identify the candidate causal factors for the problem. And then these methods can be used to confirm whether those factors are truly correlated or causal to the outcome. And then obviously, these methods are very, very heavily dependent on data. And we'll discuss that a little bit more in the next section here. So next, I want to discover some lessons learned that we've learned the hard way from working with our customers over the past 20 years or so, and how we can use these frameworks to really drill down into those root causes of performance. So the first question is, what is the best time to be gathering data? And I liken this to the question of what is the best time to plant a tree? As the saying goes, the best time to plant a tree is 20 years ago, so that you can enjoy it now. The next best time to plant a tree is right now, instead of waiting another 20 years and still not having a tree. And it's very similar with data. The best time to collect data is before you need it, so that once you get into a Kaizen event or once you're looking to analyze the process, you'll already have the information that you require. The next best time to start gathering data is right now, so that you'll have it going forward. And when you're kicking off an improvement event, the desire is to have that information there already, so that you don't need to spend those first few weeks collecting data. You don't have to have somebody standing by the line, biasing, how the process works and so forth. You don't have to take the operator out of the process. It's just, there. And so if you haven't started already, now is a good time to begin. The next question is, what data should be gathered? And how do you know in advance? And I kind of jest with the everything bagels. In an ideal world, data collection and storage would be free. And in that case, everything really would be the answer. In the real world, we have to be a little bit more focused. The first question to answer is actually, where should the data be gathered? And in general, there are a lot of ways to answer the question, but I'll focus on two scenarios. The first one is, if we know that a process is out of control, that is a really good place to start. And then also for any critical process within the operation, you should also be, starting your data collection now if you haven't already. And for each of these, you should put together an actual data collection plan for these processes. And the way that you look at that plan is you want to potentially use one of the above frameworks to hypothesize about potential causal factors, in those processes, determine what data can be collected about those different factors, and put plans in place to collect and analyze that information. And then put control plans in place to monitor those factors for any signal that you get that there are issues, and then use alerting to notify people when control limits are exceeded. And so all of those things are very easy to do once you have an Industry 4.0 system in place, such as an I-IoT system, et cetera. And we've helped a lot of companies do that type of thing. Another big issue is garbage in, garbage out. So you want to make sure that your data is clean. None of these analyses will provide any information if the information feeding into them is garbage. So part of the implementation plan for data collection should identify methods to determine when issues with the data collection itself exist. Some of the common issues that we've come across include sensors reporting anomalous results. They could be reporting bad data because they're dirty, faulty, or other reasons. Sensors not reporting any data. It could be that the sensor's broken, it could be network issues, etc. Human input issues. Sometimes you have to rely on people putting information into the process, and it could be, that they're doing kind of lazy input and just picking the first thing off of a list every time. It could be that they're missing the input. It could be unit of measure errors. We've had someone on first shift report that the percentage was 0.95, and the person on the second shift would report that it's 95%. And that makes for a really funny looking graph. And so there's other issues as well, but the key thing is to be aware of what types of errors you might have in the data up front, and put controls in place or alerts in place to notify people when there are issues with the data. And finally, talk a little bit about the role of AI and machine learning here. This is another huge subject that could be the subject of its own webinar. But at a basic level, we use these techniques to either automate or supplement the analyses that were described earlier. So just as a simplified example, when a machine learning algorithm is being used for predictive maintenance or downtime analysis, it's trying to automatically detect which variables are predictive. And so, as we collect, 100 different or 1,000 different process variables from the controller, we're trying to figure out which of those actually correlates as a leading indicator to the outcome of the machine, going down. And so the variable doesn't have to be causal to be predictive. It doesn't have to be the thing that makes the machine stop. The variable just has to be a leading indicator and correlate to the outcome. So in this case, we're not necessarily looking for a root cause. We're just looking for something that's predictive. And it's slightly different, and it might be the same in some cases, but a little bit of a twist there. But anyway, at the end of the day, everything we've discussed up to this point applies to machine learning as well. Just as an example, garbage in, garbage out is going to apply even more here than it will to somebody looking at the data. A person looking at a chart will be able to look at an anomalous reading and be able to say, okay, I'm just going to exclude that one from my thought process here. But a machine learning algorithm is going to take that as an actual data point unless you clean that data first. So that concludes today's webinar. Thank you all for attending, and let me know if you have any questions. And I do see one from Jim that asks if we'll be sharing the presentation. And absolutely, I'm going to have this posted up to my website with the video, and there will be a link there where you can download a PDF of the presentation itself. I'd love to follow up with each of you through email, but please don't hesitate to reach out to me by phone or email at any time. Those are on the screen. And I would also love to talk to each of you about how you're currently performing root cause analysis in your companies, and where you stand on your Industry 4.0 journey, and how we might be able to help. So thanks again, and talk to you next week.